Hello everyone, well here we are again, continuing with the packet, the components of matter packet, part 2. So we're going to start to look at elements and compounds. Now elements and compounds are words of course we use in chemistry all the time. You may have also seen the word element elsewhere, okay, and the word element elsewhere has different meanings. It has a very specific meaning in chemistry, okay, so we'll talk about the difference between elements and compounds. You cannot define one in terms of the other because they're both their own thing, if that makes sense, okay. Now, both of them, elements and compounds, are forms of pure matter. Anything with a formula, nice thing there, anything with a formula is classified as being pure matter. So a glass of pure water contains only H2O molecules, okay? So you can have a big old container full of stuff. If all those things, all those particles are the same, they have the same formula, H2O liquid is a glass of water. AuS, solid, is a gold bar, okay? So anything with a formula is classified as either an element or a compound, all right? Now, before we go any further, it's worth starting what I call the flow chart, okay? So get a separate piece of paper real quick, okay? And on the top, we're gonna do like a flow chart for matter. So we can write here, pure matter, all right? A little box around it. How do you know it's pure? Has formula. Okay, and we're gonna split matter into two varieties of pure matter, okay? Elements, which we'll discover their definition in a second, and compounds. All right? So there's our kind of initial flowchart. We'll come back to it in a moment, fill out some details. Okay? Now you can tell if something is either an element or a compound from its formula. Always check the formula, that's going to tell you. Okay? Now, traditionally, what we do in classes, we'll look at these different formulas, add a few more, and the students would vote, and they'd say, hey, you know, H2O element or compound, and in the past, the group always gets it right. There's always a few folks who, you know, aren't quite sure, maybe get a couple wrong, but generally speaking, the group is right, okay? So I'll just kind of go through and give you the right answers the group would come up with, okay? And then we'll decide, based on the formula, how do you define elements and compounds? All right, so first one, water. You know, if you're in class, I'd say, hey, raise your hand if you think it's an element. No one would raise their hand. Raise your hand if you think it's a compound. Pretty much everybody would go with compound and they'd be right. Okay. This one, I often get something close to a 50-50 split. Okay, so just think about this for a second, all right? In your own mind, try and figure it out. Is oxygen gas, O2, an element or a compound? Interesting, okay. The actual answer is element. As we'll discover, it's all about the nature of the atoms inside the piece of matter, not the number of atoms, okay? So it doesn't matter if it's a molecule or not. You can have molecular elements, you can have giant elements. We'll talk about those later, okay? But hey, oxygen is an element. It's a gaseous, what we call diatomic element, O2. Silver, now there might be a silver coin, there might be a trillion atoms of silver in the silver coin, but they're all the same kind of atom. We just give it the symbol Ag. We don't know how to count that many really, right? So just go with Ag, and that would be an element. Okay. Think about sugar crystal. Think about it. Vote if you like in your head. It's a compound. And similarly, carbon dioxide gas is a compound. All right, now hopefully you got those right. Okay, let's add a few more. Okay, so let's go with sodium chloride, which is table salt, right? And that has the formula NaCl. Think to yourself, element or compound? It's actually a compound. Let's do another one. Let's do, gold. Gold bar, right? Gold. Gold bar has the symbol Au, straight from the periodic table. Take a look at the periodic table. Au would be the symbol we would use to represent a gold bar. Au, of course, if you're Scottish, is a greeting. Au! That's a joke, okay? I actually speak 3 languages. I speak English, American English, and Scottish. I was in Edinburgh a couple of years ago, and I learned to speak Scottish. And to learn Scottish is very simple. You just speak English, but you add on the end of every sentence, "You bastard." So that's how you speak Scottish. I was getting on a bus, and a man behind me said, "Get on the bus, you bastard." That's Scottish. That's a joke. All right. So AU, Scottish greeting. Hey. All right. gold bar is actually an element. Okay, let's try to think of some exotic compound. Let's try and run it backwards. A compound, let's go with alcohol. C2H5OH, that's ethanol. That's found in alcoholic drinks, right? Ethanol. Is ethanol an element or a compound? It's a compound. All right. Now, question. How do we determine from the formula if they're an element or a compound? Well, look at the elements real quick. Let's do elements, right? So, element O2, element Ag, element Au. If you look at all these formulas, what they have in common is what? They contain one kind of atom. Okay, and it's called the periodic table of the elements for a reason, because each little box, and I'll probably hopefully flash a periodic table here, every box in the periodic table is telling you, hey, this is a type of atom. There's 119 types of atoms, as we know. Each one, when linked to others of its kind, is an element. Okay, all right, so an element is basically matter, and it doesn't matter how many atoms, made from, the key thing, one type of atom. That's the key thing. It doesn't matter how big that piece of matter is. It can be a gold bar with a trillion atoms of gold, all the same. It's an element, right? They're all the same kind of atom. It can be a tiny microscopic O2 molecule, two oxygen atoms stuck together, right? But it's still an element because it's the same kind of atom. Size is irrelevant when it comes to element or compound. All right, when it comes to compound, look at these. What do they have? Well, if you said, look, they have more than one kind of atom inside, you'd be right. And that's the answer. So a compound is matter made from, if you like, two or more types of atom. I should move it up so you can see it, that would be nice. So compounds, matter made from two or more types of atom in a fixed ratio. If you look, for example, at sodium chloride, there's one Na for one Cl. If you look at CO2, yeah, two types of atoms, C and O, but two oxygens for one carbon. So the formula tells you that ratio, okay? So every formula must, by definition, have a ratio of the atom type. Okay, so elements, one kind of atom, doesn't matter how many. Compounds, different kinds of atoms. Again, doesn't really matter how many, but they have to be in a fixed ratio. Okay. Now, we can further classify matter based on size. So if you go back to our flow chart real quick, we have pure matter is an element or a compound, and we can fill in some details here. So I can have, for example, carbon, just carbon atoms, we know it as a diamond, right? Just gold atoms, gold bar, or just oxygen molecules, O2. Maybe you want to go like N2 as well, that's in the air, right? So we have diamond, gold bar, oxygen gas, nitrogen gas, diatomic elements, right? Compounds, well, we had H2O, that's a good one. NaCl, that's a good one. Okay, that's big, that's small, right? Okay, so we've got our definition of elements and compounds. We can further, as I said, distinguish based on size, right? So giant is big and molecular is small. If you can see it in your hand, it's probably going to be a giant element or a giant compound. If it's too small to see, like the individual particles, it's going to be molecular. You can't see a molecule of water, right? Okay, so definitions then. So giant things are just repeating patterns of atoms or molecules. So keep it simple with atoms to start, right? So if I took a diamond, right, and there's a big old diamond you can see on your engagement ring or in, in your hand, whatever, right? Take a diamond and zoom in with that STM, that scanning tunneling microscope, so you can see the atoms, right, or image them. You'd see them arranged in a perfect kind of arrangement like this. This is called a giant repeating lattice, often called a crystal. So a crystal is just atoms that repeat their pattern over and over and over again. It just grows and grows and grows and grows. And when it gets to the point where there's enough atoms to see, you can see a small crystal, okay? A diamond is just a crystal, right? It's just a bunch of atoms of the same kind in a particular geometric arrangement, a lattice or a crystalline structure, okay? Now things that are giant, Usually have very high melting points and boiling points, right? So a giant element would be diamond. A giant element would also be gold, right? You're saying to me, well, metals aren't crystalline. Well, actually they are. If you're into metallurgy, you know about grain sizes. So if you went in with a microscope, an electron microscope, you can see there's tiny little grains in every metal. They're just polycrystalline, so there's loads and loads of little tiny crystals. That's what's in there. Okay, and that grain size is important. So when you kind of temper steel, you've seen these shows where they kind of put the sword in the water to cool it down quick. It controls the size of those crystals, which makes the edge hard or soft. All right, so metals are actually polycrystalline. There's loads of little crystals. A diamond is one big crystal, right? And you see crystals have these kind of unique kind of angles on the inside, which relate to kind of angles that are the same on the outside. All right, so so think of a diamond or a piece of gold as just a repeating pattern. Think of a floor tile pattern, right? You've got a bunch of square floor tiles. They're all the same color, right? They're all gray, right? So that's like an element. Everything is in its place, and they're all the same. However, if I think about sodium chloride, which is also a giant material, but it's a giant compound, right? Imagine a floor tile, which is a red one, blue one, red one, blue one, and that just repeats, yeah? That's a repeating structure, so it's a giant lattice, it's a crystal, but it has, alternate Na, alternate Cl. That's why NaCl is the ratio, right? So there may be a trillion of these and a trillion of these in the crystal. We don't write that. We just write the lowest ratio. That's called an empirical formula, which we'll get onto later. So giant compounds, sand and table salt, giant elements, gold, diamond. We can put gold in there. All right. Okay. So we get the idea. So if we go back to our flow chart, elements and compounds come in again two size variants. We'll kind of show you the small one in a second, but basically we have giant, and the small one in a second will be molecular. Giant and molecular. Our giant element is diamond and gold. Our giant compound is table salt, NaCl. All right, let's show you that. There it is. Okay. So moving on, let's talk about the small pieces of matter. Small pieces of matter are called molecules, right? So molecular matter, people are always talking about, are just a few atoms stuck together. Okay, so a molecule is a few atoms that have been stuck together forever. You think about our first ever lecture, I showed you making water, H plus O, we stick them together and they're there forever. It's like we superglued the atoms together and they make like that little tiny jelly bean shaped thing. Okay, that little jelly bean shaped thing is a molecule. All right, so a molecule is a bunch of atoms that have been joined together forever. The formula tells you what's inside. So H2O is a molecule that contains an H stuck to an O stuck to an H, and they're stuck inside, right? Kind of reminds me of cars, right? So you see a minivan go down the street, right? You say, hey, look, there goes a minivan. That's a bit like saying, oh, look, there goes a water molecule. You don't say, oh, look, there's an aluminum tube with a mum and two kids, right? You don't talk about what the passengers are, you talk about the thing itself. A molecule is an independent piece of matter, okay? Unfortunately, we have to name it based on what's inside. H2O is a water molecule. But when they're formed, when they've made those jelly beans, they're the things that actually move around independently and do science or chemistry, right? Okay, so definition, a molecule, two or more atoms stuck together forever to make an independent piece of matter. So molecules, water we talked about, two H's and an O stuck together, CO2, a carbon and two oxygen stuck together, we'll do this more later, but that looks like that. And then nitrogen, two N's stuck together. Okay, so these are examples of molecular materials, just a few atoms stuck together. Okay, now if we put them on our chart, molecular elements, O2, N2, molecular compounds, H2O, and if we like, we can put CO2 there as well. There we go. So that's the beginning of our flow chart. Okay, so keep that on a separate piece of paper. You'll use this to kind of classify matter later. So there's a question at the end of the packet. We'll actually classify matter based on its formula, and this can be like a guide, right? Okay. All right. Last thing, whenever you see the top hat, it's a trick. Okay, think of molecules a bit like cars on the expressway or minivans in my other example. Okay, the atoms are the passengers, the car with the people inside it is the molecule. Giant materials, think about a trip to the DMV. You have a kind of a position where you sit in the waiting room for a long period of time. That's a lattice, right? So a lot of things sitting there in a fixed position is a lattice. Okay, or a crystal. All right, it's same one. Okay, now. Chemists are all about the macro-micro thing, right? Okay, so here it's kind of a little assignment. So it's I'll just introduce it, then pause for a couple of minutes and answer it. Okay, so a microscopic view of several materials is presented below. So remember the port of call here, right? So you have your flow chart. Based on the formula, decide, hey, element or compound based on the formula, and then look at the actual material itself. Is it giant or molecular? And that kind of comes from the picture. Okay, so we have water, H2O, we have steam, H2O gas, H2O liquid for water. That's an interesting one. That's the surface of silicon, right? So a silicon chip, if you put it on one of those STM machines and zoom in, that's what you'd see. It's kind of a very interesting arrangement of atoms. And that's kind of an artistic impression of a sodium chloride crystal. Sodium chloride crystals are actually cubic. If you go to your kind of, your pantry, your larder, your shelf, with your spices and salt and stuff, get a single salt crystal, look at it, right? Get it right up to your eye and take a look at it. It will be a cube. If it's not a cube, it's several cubes joined together, and you can kind of, in your mind, kind of disassemble it to make cubes. All right, so I'll give you like a couple of minutes, so pause, right? Give me the tags. First port of call, element or compound, and then giant or molecular. All right. Okay, we back. First one, water. Water and steam are actually the same stuff, right? It's probably easier to look at this. So there's an individual water molecule, right? Okay, so that's obviously going to be molecular, and it's H2O, right? So that's its formula. It's a compound. So that's a molecular compound. Okay. Now, if I look between here and here, it's exactly the same thing. It's just the distance has changed. Changing the distance doesn't change the nature of the matter, right? If you look, sure, there's a smaller gap between them, but it doesn't matter, right? They're still individual. Pick one, that one. Still molecular compounds. Okay, it kind of reminds me, I used to have a girlfriend in graduate school who was a teacher at a Catholic school. And at the Catholic school, they used to have these things called boys coming on a bus, and they have a dance, right? And she was actually told by her superior to go around and make sure that students aren't dancing too close. She had a ruler, it's true, right? Okay, so this is how the students are supposed to dance. Students obeying the separation rules, but when the teacher wasn't looking, that's the students dancing. All right. Now, so that's also a molecular compound. Here we have silicon. Formula, silicon, right? Silicon, Si is in the periodic table, that's an element. Is it giant or molecular? Well, a silicon chip is something you can see, right? So it's a giant element. Okay. Table salt. Well, you can see it on your thumb when you look at it, right? So it's giant. Is it an element or a compound? Well, it's NaCl, NaCl, NaCl compound. So, water's a molecular compound. Doesn't care on the state of matter there. Okay. Silicon chip, giant element. Table salt, giant compound. Now there is a complication. Okay, when you freeze water, what happens? Well, it's a bad picture, but there it is. The molecules themselves take up fixed positions, and in water those positions, and it's a bad picture, are kind of like little hexagons, right? The individual molecules themselves are molecular compounds, right? But they've arranged themselves in a giant structure. So I like to call that any molecule that's made a crystal, because it gets cold enough, I call it a giant arrangement of molecular compounds. Okay, so ice would be a giant arrangement of individual little molecular compounds. Okay, now element's another good word. Okay, diamond, as we saw on the previous picture, show you back there. That's the arrangement of the atoms inside a diamond, right? And that's a bad picture because they're actually arranged like this, like these little tripods. This is called a unit cell, right? It's like a tripod, so up and down, and these guys come forward, and back like a tripod, yeah? And then you get a tripod grow off each corner, right? And eventually this will grow out, and you get that classic diamond shape, yeah? So diamonds have unique bond angles down here, which relates to crystalline angles out here. You can't get a cubic diamond, you can't get this perfectly spherical diamond. They have these classic diamond shapes for a reason. You can only cut them in certain directions, but you're cutting down lines of weakness inside the crystal when you cleave it, okay? So crystals have a larger shape based on the underlying shape of what's called the unit cell, the smallest repeatable pattern on the inside. Okay. Now diamond, the carbon atoms are arranged in little tripods, that's diamond. But graphite, the stuff in your pencil, is also carbon atoms, right? That's charcoal essentially, yeah? And in graphite, the atoms arrange themselves on these what's called graphene sheets, yeah? Which then stack on each other, right? Now the distance between atoms in the sheet is actually shorter than in diamond. So it's actually stronger that way than diamond. However, the distance between sheets is quite large, so they slide over each other and actually come off. So when you write on your page with a pencil, you're breaking this bond, right? And you're putting several sheets of graphene on your page. It's actually really, really strong, right? This way, but really weak that way. Interesting. All right. Finally, C60, and these are called allotropes. An allotrope is just atoms of an element arranged in different ways. So carbon and graphite are the classic allotropes of graphite and diamond, classic allotropes of carbon. But there's also C60, C70, that's the number of atoms, right? If I get a sheet, if I take this sheet, take it away, right, and then just fold it in on itself, I can make a ball. It looks just like a soccer ball, hexagons and pentagons, right? So you take a close look at a soccer ball, next time you see one, it's all these hexagons and pentagons stitched together. Well, put an atom of carbon at each interface, each corner, wrap it up, and you get a soccer ball, okay? And that's a sheet that's been kind of folded over on itself. You can get like rugby ball or, you know, American football shapes as well. Depends on how big the sheet is you start with. And these are allotropes of an element, okay? Carbon's kind of cool because it has 3 allotropes or more. Sulfur also has several allotropes, which is kind of nice, but they're kind of rare. All right. Now, pure matter versus mixtures. We're 6 minutes or so left. We probably won't finish, but I'll probably do the magic of magic of editing and kind of make this into one video for you just to finish. Okay. So, pure matter versus mixture. As we've talked about with our flow chart, pure matter is either an element or a compound, right? Nope, let me move it down. I'll start over. So pure matter versus mixtures. Pure matter is either an element or a compound, and then once you've decided based on the formula, you then go on size. So it's giant or molecular. Okay. So both elements and compounds can be either giant or molecular. Okay, so fair enough, that's what we've done so far. Now we're going to talk about something new. We're going to talk about mixtures. What's a mixture? Well, you think of a mixture, right? Milk. Milk's a mixture. Is it pure? No. What's the definition of pure then? Pure is something with a formula, right? So in milk, I've got water, I got fats, I got sugars, I got proteins, loads and loads of things. Those individual things, yes, have formulas, right? But when I put more than one pure thing in a container, twist it around, there's now a mixture, okay? So a mixture is any combination of pure things placed in the same container. Once there's more than one thing in there, it's no longer pure, is it? It's not just one formula, it's more than one formula, so it's said to be a mixture. So more than one formula in a container, more than one type of matter in a container, it's a mixture, okay? And you can't have a pure mixture because pure things have just one formula, okay? So mixtures are not pure materials, whereas gold, for example, would be pure because it's just Au atoms in that gold bar. White gold, which if you go to the jewelry store is kind of slightly lighter in color because you mix silver and gold together, right? That's no longer pure, that's a mixture, okay? And a mixture of metals is often called an alloy, okay? So gold and silver, white gold is an alloy. I think copper and gold is rose gold, right? Again, an alloy, all right? If I take water, pure glass of water, fair enough, just H2O molecules in there. If I have Pepsi, which is basically sugar and water, right? That's a mixture, okay? Now, when we assign mixtures, And maybe we can just add it to the bottom of our sheet here. All right. We do it in a very simple way. We can define the mixture in one of two ways, okay? And we have to do that because if we try to describe what's inside a mixture with its components, it can get very, very detailed and unnecessarily too much information. But we'll do it just for fun, right? So air is a mixture, right? Air is a mixture of gases, all right? If I wanted to kind of be specific and say what air was made from, I'd list those ingredients, right? So nitrogen, N2. What kind of material is that? Well, just real quick, get my numbers right. 78% of our air is actually stuff we don't need. It's nitrogen, yeah? So nitrogen is an inert gas. It doesn't react with anything, okay? So that's why that gas from Caesar's last breath is still around, because it doesn't get used for anything, right? But if you just had nitrogen by itself, right, what would it be? It would be a molecular element. Okay. The second biggest component of air is actually O2. That's actually 21%, right? What kind of matter is that? That's also a molecular element. Add those two up, that's 99%, right? So the remainder of air, that last 1%, has literally thousands and thousands of components, which altogether add up to 1%, right? So every time something's released from a factory or wherever, any kind of process, so, you know, methane, CO2, all these things that are made and turn into gases and evaporate all go into our atmosphere, yeah? Okay, so that remaining 1% is very complex. And I'm just going to give you a few of the things that are in that 1%, okay? Now, the third most abundant thing in our atmosphere is actually a noble gas, yeah? Now, the noble gases are on the last column of the periodic table, right? And this was actually a $1 million, no, it's less than $1 million, it's like a $100,000 question on The Millionaire Show with Regis, right? And there was your, you know, multiple choice answer, right? The question was from Regis, which of these noble gases is the third most abundant component of air? Okay, and of course this is a hard question. And what do you do? Well, the first thing you do is 50-50. Now what I want you guys to do is pick one, right? So say you're on the phone a friend at home and you're going to get that phone call, what's the third most abundant gas in the air? Just pick one, right? Okay, then we have that kind of dramatic moment when they get rid of two and they get rid of probably the one you thought, right? So it's either argon or xenon. Fair enough, right? So what do you do next? Well, you ask the audience, which is always a bad move because you always get a 50-50 split, right? And then you'll ask portal callers to phone a friend. You phone a friend, hopefully your friend's a chemist, and they tell you the right answer. Okay, it's argon. Okay, so argon, which is interesting because the noble gases, we'll talk about them more later, they exist as atoms in nature. Okay, so that's like an atomic, less than 1%. Atomic, now is that an element or a compound? It's one type of atom, element. Okay, extra credit. Why is there so much argon in the air? Okay, so if you look it up, extra credit, this is due on Wednesday, all right? So email before Wednesday, 11:59. Why is there so much argon in the air? It's an unusual thing. Why is there so much? Other things that are more obvious, right? Water vapor. Clouds are made from water vapor, not dreams, right? So when water evaporates, it cools down, it condenses. Less than 1%. What is that? That's a molecular compound. Okay? And finally, CO2, also a molecular compound, all right? And the list goes on. We'd never list them individually, right? We have to use one of those two special words. And the big question, of course, is, well, what are the special words? All right. So, quick pit stop there. I'm about to run out of time. There's my beeper. All right, I'll start again with a new video momentarily. Okay, so talking about mixtures, okay, let's go back real quick. We've determined that air is a very, very complicated mixture, right? However, I'm not going to list all its components in its description. I'm just going to use one word, and we'll get to what that one word is in a moment, okay? So we'll save that for later. But for now, I just want to go back and just recap something, okay? So I've got a little task for you, okay? Remember that slide I showed you with the silicon chip and you just labeled the types of pure matter? Now I'm going to show you a slide with different kinds of matter on it. I want you to do the same thing, okay? All right, but there may or may not be some mixtures on there, okay? So I'm gonna go old school here, all right? So there we go. How would you describe that matter? How would you describe that matter? It's just a bunch of atoms, well separated, hint, hint, right? Well separated atoms in a container. What would you say that was? Well, they're all the same kind and they're well separated. So, atoms of an element. It might be helium, neon, something like that, one of those noble gases. Okay. Remember, you have the power of the pause, right? If you need more time, just pause. All right. Next one. Look at that one. That might be, for example, nitrogen, right? So we have two atoms of the same type. Color denotes type of atom, right? So two atoms of the same type stuck together. That makes these all diatomic molecules. Are they a gas, solid, liquid, or gas? Well, they're well separated, so they're probably a gas, right? So what would you say that was? If you said molecules of an element or molecular element, you'd be correct. For whatever reason, this slide is talking like Yoda. Molecules of element you are. Sorry, I can't help myself. Molecular element. Okay. Next one. What's that one doing? Well, it's got an atom surrounded by three others of the same type, so it's 1 to 3 ratio. So it's a compound, fixed ratio, different types of atoms. They're a gas because again they're well separated. What is it? It's molecular compound or molecules of a compound. All right. Now finally, last one. Put them all in a jar. What do you get when you put them all in a jar? You get a mixture, right? So that's just like air, right? That's just like air. That's the different components of air, maybe, right? What do we call that? Well, if we listed the components, a mixture of elements and compounds, but we never do that, right? So scratch that out. How would we actually define what that is? So this is where we get into that word, okay? So mixtures are defined as being either, and these are the key words, homogeneous or heterogeneous. So it's one word description, right? But what's the definition of the word, right? Well, think about it. Genius just means phase. And homo and hetero means same or different, right? Okay? So homogeneous, same phase. If I thought what that means, same phase, it just means it's smooth all the way through, right? If it's hetero, it's different. It's lumpy, right, all the way through, okay? So homogeneous mixtures, if I use some book definitions, uniform, smooth, throughout. Heterogeneous mixtures are non-uniform, lumpy, if you like, throughout, all right? So let me give you some examples. You can tell me if this is a homogeneous or heterogeneous mixture, okay? Fresh milk. Now, it doesn't matter what's going on the microscopic level, it's what it looks like in your hand. So these are macroscopic determinations, right? So look at a glass of milk. Is it the same all the way through, or can you see different areas of different stuff? Well, fresh milk's the same all the way through, right? So that's fresh milk. It's homogeneous. Fresh milk's homogeneous. What about stale milk? So I forget to put it back in the fridge, come back a week later, pour some out into a glass, I get a liquid and a lump. Liquid, then a lump. Is it smooth or lumpy? It's lumpy, right? It's heterogeneous. Stale milk. All right. How about no pulp orange juice? Is it the same all the way through, or is it lumpy? It's the same all the way through, looking at the glass, right? So no pulp. OJ. is an example of homogeneous mixture. What about lots of pulp orange juice? Does anybody actually drink that stuff? Lots of pulp orange juice. I tried it once. It felt like someone had thrown up in my mouth. Just me. Right? So think about it. Orange juice, pithy bit. Orange juice, pithy bit. So liquid, solid, liquid, solid. It's lumpy kind of, right? Okay. So that's hetero. Lots of pulp. OJ. All right. Finally, let's think about flat Pepsi versus fresh Pepsi. When I have fresh Pepsi, I have lots of bubbles, right? Now, when I say lumpy, that doesn't tell you it has to be solid and liquid, it just tells you a whole different phase, right? So I can have gas and liquid rather than solid and liquid. So fresh Pepsi with lots of bubbles is heterogeneous. Stale Pepsi or flat Pepsi is homogeneous. Okay, nice. All right, finally, let's go back to the air. What do we think? Do we think air is homogeneous or heterogeneous? What do we think? Air, if you think about it, does this piece of air look like this piece of air? Yes, it does. It's homogeneous. So air is a homogeneous mixture, yes, of all those things, but we don't list the ingredients because it's just too many. Air is a homogeneous mixture. Stale milk is a heterogeneous mixture, if you get that. Okay, so interesting question. We kind of touched on it already. Can something be both a solid and a homogeneous mixture? If I get some sand and gravel, right, and turn them into cement, that's a heterogeneous mixture. Oh, there's a piece of sand, there's a piece of gravel, right? Okay, but can it be smooth? Can I mix things together and then have a mixture of things and then have it be smooth if it's a solid? Well, the answer is yes, okay, because that's exactly what an alloy is. So bronze equals copper and tin. Okay, so take some copper and tin, put them into a container, heat them up so they all melt together, and stir them around. They become a homogeneous mixture, and just cool it down and it becomes a solid. Now bronze is really interesting because bronze is used a lot for statues. Why? Because it's one of only 2 or 3 materials that expand when they freeze. Okay, so I go from liquid metal to solid metal, that's freezing, right? And it expands. So if I got like a mold, it expands into all the nooks and crannies. It makes for a really great statue. Okay, so bronze is an example of an alloy. We talked about white gold, which was gold and silver, and then rose gold, which was gold and copper. These are all alloys. Oh, I said it already. Alloy. All right. Maybe you've seen. And it's kind of interesting actually because alloys tend to take the properties of the things they're composed of actually in the alloy, right? So, for example, white gold looks a lot like real gold, right? Bronze looks a lot like copper and conducts electricity really well, just like copper does, okay? Now, if you go down to the place where all the teenagers hang out with their cars, used to be the mall, right? But anyway, and they all have their souped up cars, right? Or some Honda Civic or something, right? And there's all those shiny parts on it, right? So there's like a shiny chrome bumper or wheels or something. Chrome's really expensive, but they buy it because it's shiny, right? Okay, you can get away with a cheap alloy shiny thing. Ever heard of mag alloy wheels, right? They're super shiny, right? They're aluminum and magnesium together, which tends to stay shiny. All right. All right. Extra credit. Again, I'm giving you 3 now, right? Give me a couple of alloys, not ones we've talked about. Type them in, send them to me in his email with your other ones, your other extra credit. By, 11:59 Wednesday, as the other ones. All right. Now, here's a quick flow chart. It's kind of combined the ones I've already done. Well, let's finish off the one, right? So we talk about our mixtures. We have homogeneous, heterogeneous, uniform, non-uniform. Okay, so what we got here is a mixture flow chart. It's either homogeneous or heterogeneous, just based on a macroscopic observation, and then our previous pure matter has a formula flow chart. Okay, I found this in one of the books. I like it a lot because it has that whole macro to micro thing. So matter, variable composition, that means, hey, is it a mixture, yes or no, right? If it's just one type of particle that goes over here, it's got a formula, right? So that's, formula. So that's a pure substance. If it's not got a single formula, it's a mixture of things, it's a mixture, right? And then we have elements and compounds, heterogeneous, homogeneous. Okay, so if I look inside the Goodyear blimp, that's got helium in it, which is an atomic element, right, in the gas phase. If I look at a glass of water, we saw that already, there's my water molecules, pure water, just all the same, right? Now this is where it gets interesting. There's a cup of tea, right? And tea's a bunch of things. There's my big old kind of like flavoring molecule surrounded by water. So, you know, maybe that's caffeine or something, right? There's water and caffeine, that's a mixture. When you look at it, is it smooth all the way through? Yes, it is, right? So it's smooth all the way through just looking at it, so it's homogeneous. Now here's a beach, so there's the sand, there's the water, that's where they meet. That's a heterogeneous, that's a solid, and that's a liquid, so a different phase, right? Sand and water in a bucket, you can tell the difference. All right. Now, at the end of the packets, I like to finish with a couple of good practice questions, things like you'd see on your test, okay? So what I'd like you guys to do, okay, pause after I finish talking, right? Give it a pause, and then try and answer these questions, okay? And then I'll go through them, okay? And then we'll do the same thing on the next page with the odd exam, all right? So pause, come back. All right, you're back. First one, the compressed gases in a deep sea diver's tank, right? Helium and oxygen. Well, obviously that's a mixture because it's two things, right? Two things with a formula, mixture. And I'm going to say it's homogeneous, right? If you let that stuff out, it's a clear colorless mixture of gases, right? You can't tell the difference, right? Ham and cheese omelette, obviously that's a mixture. Whenever you have food, all foods are very complex mixtures on themselves, right? So ham's got protein, fat, and other things in it. Cheese, fat, protein, carbs, all kinds of stuff, right? So that's a mixture of mixtures. So foods are always a mixture. Is it homogeneous or heterogeneous? Well, ham, egg, cheese, egg, right? So it's hetero. Okay, because you can see the different parts, right? How would you turn an omelette into a homogeneous mixture? How would you turn any food into a homogeneous mixture? Put it in a blender, right? So baby food is homogeneous. Grown-up food is heterogeneous. Ice cube, made from water, right? So that would be H2O solid as a code, chemistry code. So that's a molecular compound. Okay. A ruby, now this one's interesting. Okay, a ruby is basically glass, aluminum oxide is glass essentially, right? And there's these little gaps in the pattern, in the lattice, and you can put some chromium impurities in there and they absorb light, make it red, okay? So it's two things. It's two things, and this is a variable, right? This can be a lot to be like a dark red ruby or a light to make, you know, less, right? So that's a variable amount. So it's not a fixed ratio, so it's a mixture, right? Two things, it's a mixture. Is a ruby homogeneous or heterogeneous? Well, it's kind of smooth all the way through, mixture, homogeneous. Fair enough. All right, I'm full of extra credit today. Full of extra credit today. So here, asking about the separation of mixtures. So we talked about mixtures. You can read forward a little bit. It's coming up in a future packet. But let's just talk, right? So see if you can figure, you can look in the book or you can look online, whatever, but try and figure it out yourself if you like, right? This is a kind of a story from childhood. I went to the beach when I was a kid, right? There's me, there's the ocean, which contains H2O and NaCl dissolved, and there's the sand, SiO2, right? So I'm walking along the beach next to the water, the salt water, right? I dragged the bucket through the surf, and I've got some sand in the bottom, which is SiO2, and then I got some NaCl, aqueous dissolved, and some H2O up here, right? What I want to do is separate this out into a jar of dry sand, a glass of water I can drink, and a thing of table salt. Okay? So I want three separate components from this complicated mixture. Okay, now this is kind of great because we're going to do one of our labs very shortly is separation of a mixture, and when we'll put some numbers on this. But you can kind of figure it out yourself, okay? You can do the little bit of reading in the book if you want to get an idea, or you can probably just kind of MacGyver it yourself. How would you, using your kind of intuition, separate these things out into three containers? I don't want to lose any, right? So if you can't evaporate off the water because you lose it, right? So plus 3 extra credit again by Wednesday at 11:59. All right. Finally, our last page. This is an old exam question. Okay. Now, on the exams, you're going to have me just send you the exams, and you're going to have 24 hours to do them. But in a classroom, you'd have like 10, 15 minutes per question. So, pretend you're in a class. Give yourself 10 minutes and try and answer this question. State whether the following are elements, mixtures, or compounds. Extra detail is really those describing words. So, element, mixture, or compound for full credit. Giant, molecular, extra credit for that. Homogeneous, heterogeneous, extra credit for that. Okay. Okay, pause. You're back? All right, diamond, that's obviously an element, right? And it's giant. Now on the test, I'm only going to grade maybe the first 2 or 3, right? So only put the extra detail when you're sure. Air, we did that one already, that's a mixture. That's homogeneous mixture, right? Homogeneous mixture. Water, well, on the more recent tests, if it's pure, I'll give you the formula. So water, H2O, pure, that's a molecular compound. Oxygen gas, O2, that's a molecular element. Carbon dioxide gas, again, I'll give you the formula, that's a molecular compound. Cup of coffee, interesting, right? If it's this stuff, right, it's like a brown liquid, right? So it's obviously a mixture. There's kind of all kinds of stuff in there, right? So it's a mixture, but it's homogeneous. It's kind of the same brown goop all the way through. If I went to Starbucks, right, and I got my latte with the foam and the sprinkles and the umbrella, that's actually heterogeneous because the sprinkles are a solid and the coffee is a liquid. Okay, so it depends on the sample. I wouldn't do that one for extra credit if I'm only going to get 3 points first 3, because you've got to kind of really define what kind of coffee you got there. Sand, assuming it's pure sand, SiO2, that's a giant compound. Okay, so hopefully that makes sense. Okay, so that's a nice little example of kind of the exam question. Okay, so it's a while before we get to the exam, but a question like that will probably be on there. Okay. All right, so we're going to stop there. I'll get this loaded, and I'll see you on the next one.